Hi guys, for today's lesson we're going to be dealing with exponential and logarithmic graphs with transformations. So first up, what is an exponential graph? So it's a graph with the equation form y equals a to the power of x, or y equals a to the power of negative x, where a is a positive number like a constant. So with exponential graphs, the main thing to understand is that you need to have your variable x as a power. If your x is not a power, it's not going to create this sort of graph. So what do these graphs look like? So first up, for example, y equals 2 to the power of x. There's our power of x, which is required. We've got this asymptote towards the x-axis for our negative values of x. And for our positive values of x, it shoots up to infinity. You can see here from our base of 2, it gives you this 0.12. That y value there is going to come from our base. And similar with this, you can see the base of 2 down there with our x value of negative 1. This graph of y equals 2 to the power of negative x, when our power is a negative version, it's very similar to this. It's pretty much just a mirror image along the y-axis. So this part here is literally just switched over to here, as you can see here. And this part here switches over to the other side of the y-axis to look like that. Okay, next up, logarithmic graphs. They are graphs with the equation form y equals log base a to the x is being logged, where a is some sort of positive base. And they look like this. So you get this asymptote going towards the y-axis to the negative values of y. And this part here does eventually go up and up and up to infinity, but it goes quite slowly. This base 2 with the log kind of indicate, like, it shows you how these points come about. So with the y value of 1, that base of 2 goes there, and similar with this this point 1/2 to negative 1. If we change our base to a 3, we get, instead of the 0.21, we get this 0.31. So similar sort of patterns happening, and these graphs do look quite similar, or very similar. Note the functions y equals 2 to the power of x and y equals log base 2 to the power to the x are inverse functions, i.e. they are reflections of each other about the line y equals x. So what I mean by that is, if I graph these two functions, which are very similar because they both have this base of 2, then we can see that they are reflected across this line y equals x. You can see that these points are pretty much straight across from each other, across that line, and I could do that for as many points as I like with these two equations. Another way to look at it is to see that the points are literally just being swapped around with each other. So if I swap the 1 and 2, I would get this point right here. It's reflection. And similar with this point and this point. So a really important property for inverse functions. So some rules to remember. We can apply changes or transformations to the equation of a graph in order to slide or reflect a graph around the number plane. So the idea is you need to be able to take these sorts of graphs, and you need to know how to move these sorts of graphs up, down, left or right to be able to reflect it across the y-axis, or reflect it across the x-axis, or to stretch it or to shrink it, etc. And these changes that we're talking about, they're called transformations. So the first transformation that I want to teach you is the vertical sliding. So the rule is to add or subtract a constant to the end of the equation to slide it up or down. So for example, I've taken this graph and I've literally decided to slide it down by 5. I've minus 5 from that equation. And you can see that this is literally moved straight down by 5 squares. So like if I grab this original equation, so if I grab that, I can slide it back up to look like what it used to look like this graph over here. But if I move it back, if I slide it down, it looks like that. And you can see here that this point here, 1, 2, has literally been slid down by 5 to go to 1 minus 3. So that's how I got that point. It's like 2 take away this 5 gives you my minus 3. Okay, next up, sliding to the left. So the rule is to change the variable x to x plus a. Really important that when you've got a plus in there, it's going to be going to the left, where a is some sort of positive value. So for example, here's my function y equals log base 2 to the x. If I change my x to say x plus 3, that 3 is saying sliding to the left by 3. So what I've done is I've grabbed this line and I've literally just pushed it to the left by 3 squares, and I get something that looks like this. So very similar, it's just moved to the left. You can see here that this point 21 has literally moved to make negative 1, 1. That 2, if I move it to the left 3, if I minus 3 from it, it goes all the way to this negative 1. Okay, so moving on. Next up, if I want to slide to the right, so I need to change the variable x to x minus a. So remember, going to the right, it needs to be a negative number here, so where a is some sort of positive value. So for example, if I want to move this function to the right, I need to change that x, and that x alone, I don't worry about the negative. I need to change that x to something like x take away a number. So let's do, say, x take away 4. That means I'm sliding to the right by 4. So if I take this line and move it to the right by 4 squares, it goes and looks something like this. You can see here that this point negative 1, 2, that's going to move to the right by 4. That negative 1 is going to go all the way over to make a positive 3. As you can see here, it becomes that positive 3. The y value of 2 doesn't change. So that value of 2 can still come from this base number right here. Okay, so moving on, what about a reflection about the x-axis? So the rule is to take the negative of the entire function. So if I want to reflect this about the x-axis, I need to I need to literally put a negative with this whole thing. So like what I've got here. In this case, I technically don't need the brackets because there's only one term that I'm making negative. If there was 2 terms in my function, I would need to put brackets around the whole lot. I'd need to make everything negative. Okay, so what does that look like? Well, literally we just swap everything around the x-axis. So this part of the function down here literally just goes straight to the other side of the x-axis. Instead of going down, it points up. And this point here, instead of pointing kind of to the right, it's going instead of pointing up this way, it's instead going to point down here, as you can see. And in terms of points, this point here, which is 2, 1, that's literally just going to get swapped to the other side of the x-axis. So instead of positive 1 for the y value, it's going to be negative 1. The next one is to reflect about the y-axis. So the rule is to change the variable x to negative x. So for example, if I want to reflect this about this axis here, I'll go change this x to its negative version, negative x. And you can see that when I do that, like this part here literally just gets swapped over to this side, as you can see. And same thing with this, it just goes straight over here. So it looks like that. And you can see here that I've got the point 3, 1. Well, that's literally going to get swapped over. So instead of positive 3, 1, it's going to make negative 3, 1 for my point. And you can see here that's the x-intercept of 1. It's instead going to be an x-intercept of negative 1, as you can see there. Okay, moving on. What about stretching or squashing an equation? So the rule is to multiply the entire function by a positive value to stretch it or to squash the graph. So the idea is if you want to multiply by a number larger than 1, it's going to stretch it. And if you multiply by something less than 1, it's going to squash it. It's going to make it kind of shrink a little bit. So for example, this equation right here, y equals 2 to the power of negative x, I've decided to kind of stretch it. I've decided to multiply it by 3. This 3 with a dot, that dot is a symbol for multiplication, so it's multiplying this function by 3. So the idea is that, say, this y-intercept of 1, instead of being at 1, it's going to be multiplied by 3. It's going to go all the way up to a y-intercept of 3. It's kind of been stretched out. And and another version, like say this point right here, -1, 2. That value of 2 is going to be multiplied by 3 as well, only the y values, and it's going to go all the way up to a y value of 6. So it's going to be -1, 6 for that point, etc. So you can just see that all the points along your line are literally is going to get multiplied by 3. They're going to stretch right up. So it's going to go up a lot quicker because everything's being multiplied by 3. Notice that the x values do not change. Okay, let's just do some harder examples. So sketch the following curves and state their domain and range. So let's have a look at this one right here. So y equals negative log base 5 to the x plus 3. So the tricky part about this sort of function here is that there's lots of different transformations. You've got to apply this transformation of x plus 3. That means move to the left by 3. And this negative out the front means that it's being reflected about the x-axis. So let's go through this strategy here. Okay, so step 1, we need to firstly just graph the basic function. So I look at this and I think log base 5 to the x. We can just do that nice basic one. So a typical log function just looks like this, log base 5 to the x. So I'm kind of ticking off that I'm doing log base 5 and the x, but I've got to do the other transformations. So first up, let's reflect it about the x-axis. Let's do this negative. You can do them in any order you want. So literally that gets reflected, so it looks like that instead. And now I'm going to deal with this plus 3, which is moving to the left by 3. So I'm literally going to grab that equation, I'm going to slide it to the left by 3, and I get something that looks like this. You'll notice that this asymptote here has to get moved over to the x minus 3 line. So we get this sort of looking equation in the end for our desired function. The domain of this is literally going to be all our x values, so it's going to be everything bigger than -3. It's definitely not going to be equal to -3 because it just gets closer and closer to it. It doesn't ever get to that asymptote. And our range is going to be literally all values of y. This is definitely shooting up to infinity, and this, even though it doesn't look it, will eventually get all the way down to -infinity as well. Okay, so moving on, one more. This one's a bit trickier. We've got 3 different transformations. We've got the negative x transformation, which is reflecting about the y-axis. The negative reflection here is reflecting about the x-axis, and the -4 constant is going to slide it down by 4. You definitely want to do this transformation last, so I suggest doing this one or this one first. So start with your basic log base 2 function, so y equals log base 2 to the x. Start off nice and simple with that. Next up, let's reflect over the x-axis, doing this one here, this negative. So then it looks like something like this. Remember that part there just goes underneath there, and this goes all the way up. Next up, let's do the negative x transformation, reflect over the y-axis. So this part here is going to jump over here. Oh no, did I stuff that one up? Oh no, sorry, over here, yeah, my bad. So this part here is going to jump over here, sorry, because we've got to deal with this one now. And then this part here is going to jump over to this side, so it's going to look something like this. So we've done the 2 transformations. And then lastly, we're going to do the final part, which is the -4, and that's sliding it down by 4. So this point here, for example, -2, -1, it's going to go all the way down to -2, -5. That -1 is minusing another 4. So it gets down to this point here. So it literally just gets slid down into that sort of position, and that's when we are done. Now let's have a look at the domain and range of this function. So you can see here that our x values are going to be all these negative values here. It never gets to this side, so x has to be less than 0. And for our y, we can see that we've got all positive y, it goes all the way up to infinity, and these will eventually go all the way down to -infinity. So it's going to be all real y for our range. I hope this helps. Good luck with the question.